Hello guys, myself Girish. I'm studying in Sri Venkateshwara College of Engineering, Bangalore from the Department of Information Science and Engineering. Today we are going to discuss about the most important topic in ADA, that is Introduction to the Knapsack Problem. The topic Introduction to the Knapsack Problem. First we discuss about the introduction of this. The knapsack problem is a classic optimization problem in computer science. It involves maximizing the value of items selected from a set of items. Subject to a weight constraint, this problem has application in diverse fields such as resource allocation, logistics, and financial planning. Next, defining the knapsack problem. The knapsack problem is a fundamental optimization problem where a thief or hacker needs to choose items to maximize the value of their loot or their backpack contents respectively. The 0 or 1 knapsack. Each item can be either fully selected or left behind. There is no partial selection allowed. The fractional knapsack. It seems can be partially selected, allowing in thief's choice of an item to maximize value within the weight constraint. Then the knapsack algorithm in ADA. The knapsack algorithm means its problem is solved by dynamic programming techniques. The dynamic programming breaks down the problem into smaller subproblems and solves them into a systematic way. First one, initialization. Create a table to store the maximum value achievable for each weight to the knapsack capacity. Fill the table iteratively considering the value and weight of each item and the current weight limit. Then backtracking. After the table is filled, track back to find the optimal combination of its they maximize the values. Implementing the knapsack algorithm. Implementing the knapsack algorithm in ADA involves using data structures such as arrays and loops to iterate through the items and calculate the maximum value achievable for each weight. For example, greedy algorithm is used to select items with the highest value to weight ratio first. Then dynamic programming uses a table to store the maximum value achievable for each weight up to the knapsack capacity. Then time and space complexity. The time and space complexity of the knapsack algorithm depends on the specific implementation and the size of the input data. Generally, the dynamic programming approach has a time complexity of O n into W, where n is the number of items and W is the knapsack capacity. Time complexity 0 n into W for the dynamic programming approach. Space complexity 0 into n into W for the dynamic programming approach. Time and space complexity both are same here. Next, optimizing the knapsack algorithm. Optimizing the knapsack algorithm can improve its performance and reduce its computational demands. Techniques for optimization includes using memorization to avoid redundant computations and reducing the size of the search space. Memorization store the result of subproblems to avoid recalculating them. Branch and bound prevent the search tree by eliminating subproblems that cannot load to an optimal solution. Handling constraints in the knapsack problem. The knapsack problem can be modified to include additional constraints such as items densities, deadlines, and volume restrictions. These constraints need to incorporated into the algorithms to achieve an optimal solution. First one, item dependencies. Certain items may only be selected if other items are also included. Deadlines. It's it means items may have deadlines, adding time constraints to the problem. Volume restrictions. The knapsack may have a maximum volume limit in this. Next, application of the knapsack algorithm. The knapsack algorithm has numerous applications in real-world scenarios. It can be used to optimize resources allocation, logistics, and financial planning. Logistics, optimizing delivery routes and packing vehicles with goods. Financial planning, selecting investments with the highest potential return with a given budget. Resource allocation, optimizing the allocation resources such as bandwidth, memory, or processing, etc. Then limitations and challenges. The knapsack problem can be computationally complex, partially for large input sizes. Additionally, it can be challenged to handle real-world constraints that are not easily modeled in the standard problem formulation. Computationally complexity. For large input sizes, the time required to find the optimal solution can be significant. Real world constraints. Modeling complex real world constraints and can be challenging. Then the last one, conclusion and future consideration. The knapsack problem is a fundamental optimization problem with numerous applications in various fields. Future research directions include developing more efficient algorithms for handling large input sizes and complex constraints, as well as exploring applications of the problem in emerging areas such as machine learning and artificial intelligence.